All right, everyone, welcome back. Welcome back. Now, we have finished our section on line integrals and applications. Okay. Now we're moving into a new section called surface integrals. Okay, surface integrals. Now, in the previous section of this course, we learned how to integrate over curves. Okay, integrate over a curve that sits in, say, 2- or 3-dimensional space. Right? It seems natural to ask the question, well, can we integrate over surfaces? Can we go up 1 dimension and integrate over surfaces?
When we did double integrals, wasn't it? Integration over the surface.
Yes, when you did double integrals, you were integrating over a surface. That's true. Can anyone tell me what's special about the surface of integration that you were integrating over?
Because now we're doing surfaces in 3 dimensions that are not just flat, whereas the double integrals are 4.
For example, yes. So for example, double integrals, right? The region of integration, yes, it's a surface, but it sits in the xy plane.
Yeah.
Okay.
Like line integral and curve.
Correct, right? You're like, it's just a generalisation of what you know. All right. So today we're going to motivate the subject a little bit. We're also going to talk about parameterized surfaces. Okay, and you can think about drawing analogies with parametrizing curves. Okay, we know how to parameterize, for example, the unit circle. How can we parameterize surfaces? Okay. Just to get back to your comment about double integrals, we will see double integrals in this section as well. So we're headed in the direction that, okay, we want to integrate over surfaces. And to do that, we're going to break it down to the evaluation of double integrals with a special integrando. Okay? All right. So, where are we going? Well, we're going to learn about a surface integral. And the important thing here is how and why is it useful? Well, one great application is finding surface area of a surface. Now, I'm not sure at school or possibly in first year you learned techniques to calculate the surface area of a given surface. Okay, just using single integrals. Anyone remember that? Yeah. Okay. Some people do. Yep. So this is a generalisation of that idea. Right. The second very important thing as far as applications go for studying surface integrals is to calculate flux. Now, you may go, okay, but hang on, didn't we already calculate flux? Yeah, we did, but that was in the plane. Okay, and we were looking at something like this. We were saying, okay, here's a circle in the plane. What's the flux over the circle? Okay, what surface integrals allows us to do is look at flow over 2-dimensional regions. Okay. All right. So let's have a look at what we call a parameterized surface. All right. Okay, you can think of this vector function phi as mapping this, in this case, this domain to some sort of surface. Okay, so here this is how we write our parametrization. And you can think of this coordinate system, or actually it's referred to as curvilinear coordinates. Okay, now you've seen a number of coordinate systems already. You've seen, for example, the spherical coordinates. You've seen cylindrical coordinates, right? You've seen the regular rectangular coordinates, polar coordinates. Okay, curvilinear coordinates is a generalization of all of these. Okay, so the coordinate systems that you've already looked at are special cases of this curvilinear coordinate setting. Okay, so geometrically, you can think you've got some domain, some two-dimensional domain, that gets mapped to, so you get a surface that sits in R3. Okay, so the best way to get comfortable with this is to, A, review the coordinate systems that you already know. Okay, you need to be comfortable with spherical and cylindrical coordinates and polars as well. But also just look at some examples. So that's essentially what we're going to do today. All right, so here's an example. The easiest example here is just to have a graph. All right, so this is the type of surface that is very common. A graph of this type has parametrization, as you would expect, given by this phi here. Now, you can think of this as a generalization from what you already know, a function of one variable, okay, to a function of two variables. All right, so geometrically, you can see this is our parameter domain down here. And it lies below the surface, okay? So you can think of that surface projecting onto D, all right, or casting a shadow on D. Right, so that's the easiest parametrization. What about something else? Well, the cone has the following parametrization. Okay? Anybody know what system we're working in there? What's the coordinate system? Cylindrical, right? So okay, if you write it without the use of V's, you can have, you know, R and theta here. So you would have R there, theta there, R there, theta there, R there, if you prefer that. And I'm going to switch between the two, okay? All right. Cylinder of a fixed radius. How can we describe that surface? Well, remember, this R here is fixed, right? You would think that you would use cylindrical coordinates for this one, because it is a cylinder after all, right? But what's happening here geometrically? Well, this domain here, or this little rectangle, is getting wrapped around the cylinder, okay? And you can see this vertical line under the map becomes this vertical line. This horizontal line under the map becomes a circle that bounds the cylinder. Okay, so again, we're in cylindrical coordinates here. And you can see that the rectangle wraps around the cylinder. Okay. Now, of course, to verify, how do I know that this is actually a correct parameterization? Well, if you're given the parameterization, you can just take the components and put them in here and see if the equation actually holds, right? All right, let's talk about the sphere with a fixed radius. Okay, well, here the surface of the sphere is given by this parameterization. Okay, again you can check that. So we're working in spherical coordinates here. Right, now remember in spherical coordinates, you've got two angles and a length. Okay? One of these angles, I guess it sits in the xy plane. The other angle measures how far you come down from the positive OZ axis. Okay? But because we think of this R in this example to be fixed, there's only two variables here. Okay? So okay. So what's happening here with the parameterization? It's quite interesting, actually. The rectangle is getting wrapped around the sphere, okay? And this line and this line, they form longitude and latitude on the sphere, okay? You may think, well, what happens to these edges? Well, the top edge and the bottom edge, they collapse to the North Pole and the South Pole, respectively. Okay? So the rectangle wraps around the sphere. Okay? And the top edge and the bottom edge, they collapse at the poles. Okay, so again, note that this line here becomes a latitude line, and this line here becomes a longitude line. All right, so where are we going with this? Well, our main goal in introducing these parameterizations, of course, is to set up this surface integral. Okay? And to do that, we need to, I guess, we need to approximate, for example, the surface area in some way. To do that, we introduce something called grid lines and grid curves. Okay? So on this, you can think of this as the domain, the parameter domain of your parameterization. Okay? And each of these lines, each of them is called a grid line. Okay? Now, you can see this line here, under this parameterization, gets mapped to this line here. So the straight line gets mapped to a curvy line in this picture. This pink line, the same. All right? Now, the lines that are mapped to by our parameterization are called grid curves. Grid curves. Okay. Now, let's consider fixing one of the variables in our parameterization. Okay? So along this pink curve, you see that the first variable, the u variable, is fixed. Right? Along this curve, we're fixing the second variable. Okay? Now if we do that, we get a map, and we can obtain a tangent vector to the curve. Okay? So what we're doing here, we've got two curves, and we're going to use partial derivatives to formulate a tangent vector to each curve at this point P. Okay? Now you might think, why do we want to do that? Well, the basic idea here is to get these tangent vectors, and then once I have the tangent vector to a surface, then I can do things. For example, I can take the dot product and form a normal vector. And that's going to be quite important for our study of surface integrals. Okay? All right, so what do we mean when we say this tangent vector? All we do is we differentiate the components of our parametrization with respect to u in this case, right? So here we mean oh, hang on, sorry. Let me start that again. So okay, so if this is our parametrization here, then our derivative here is just the following. Okay, so we form a new vector there. Right, so similarly for the other case, we just form a new vector by I've done it again. Differentiating with respect to v in a component-wise fashion. Okay, so as long as we have a nice smooth surface, then we can always get these tangent vectors, right? Okay. So what do these things look like? Well, here we've got some grid lines drawn in. Think of this as your parameter domain. Right? Here's the surface that is parameterized by this phi. You can see there's two tangent vectors there, right? And in the picture, there's a normal vector as well. Okay? Now, you need to be careful with the notation here. Yes, n's a normal vector. N is not necessarily a unit vector. All right? N is obtained by taking the cross product of our two tangent vectors. Okay? As long as you remember your right-hand rule, you can find out which way n's pointing. All right? So in this case, it would be what's going to be tu cross tv, right? So be careful with the notation in this section. When you see the vector n, it's not necessarily a unit vector. And secondly, these tangent vectors are not necessarily unit tangent vectors either. We've worked with unit tangent vectors when we did line integrals, but here there's no hat. Okay, that's why it's very important to distinguish between these two cases. Okay. All right, so here's an example. here's some grid curves drawn in. And here we've got some tangent vectors, and you can produce a normal vector to the surface. Okay, so let's do an example. Okay, so you might need a scrap of paper for this. Consider the paraboloid given by the image of this particular function, right? Show that we can parameterize the paraboloid by the following vector function. Okay, so it's pretty easy. All you do is you show that the respective components of parameterization satisfy this. Before we do that, though, can anyone think of another parameterization for this paraboloid? Anyone? Sorry? Oh, it might do it, but there's even a simpler one than that. Yep. That's right. This is actually it's a graph, right? So that's important. Okay, so you can use this, but it's a bit exotic. You would probably use a simpler parameterization than that. Okay, so note our surface is a graph. So the following parameterization would do. Okay, so you should choose the simplest parameterization, really. This one's given to you, but let's actually answer the question. Okay, so here we've got x, y, and z. All you need to do is put these in and show that star holds. Okay, so all right, so it's quite easy. All you use is cos squared plus sine squared, right? So cos squared plus sine squared equals 1, right? So okay, 1 minus r squared cos squared. Okay. All right. So let's calculate the tangent vectors and try to interpret what they mean here. Okay, what do they mean? That's what I'll do. Right, so I'll just start again up here. Tangent vectors. Okay, so we differentiate in the component-wise fashion. Something like that. And the other one's going to be something like minus r sine theta, r cos theta, 0. Okay, so you can see that this bottom tangent vector, it lies in the planes that are always parallel to the xy plane. Okay, the z component 0 there. Now, if we wanted to produce a normal vector, we would just, of course, cross these two things together. Okay? So let's just take a quick look at what's going on here. Okay, I've really just drawn in the top part of the paraboloid. Okay. Right, so the part of the paraboloid that stays above the xy plane. All right, here's another simple example. Consider the sphere. Show that this particular vector function parameterizes the sphere. Okay. And what are the tangent vectors? Now, I'm not going to bore you with actually verifying that. So, oops. So I invite you to do that on your own. All right, the next question is, what are the tangent vectors? Okay, again, just take the partial derivatives as you would. Okay, so we're going to produce a new vector function here, which is going to be, what's it going to be? So I'm going to take the 2 out the front. So we're going to get minus cos theta, oh, no, plus, sorry, cos phi. And move on to the next one, minus sine theta, cos phi, and then over here we're going to get minus sine. All right. So move on to the next one. Differentiate component in a component-wise fashion with respect to theta. So again, I'm going to take the 2 out. Zero. Okay, so you may look at this and go, okay, well, this is pretty easy. The important thing here is that you need to get comfortable with parameterized surfaces. You need to almost recognize them and be able to come up with them as you would functions of one variable, okay, or curves and paths in R squared and R cubed. Okay? A lot of students find it quite challenging because there's a lot of different coordinate systems at work. Okay, so review spherical coordinates, review your cylindrical coordinates. Okay, and like I said, the whole aim here is to use these tangent vectors to approximate surface area. So what do I mean by that? Well, let me just give you a little glimpse at it. Okay, so I'll come back to that later. All right. See this parameter domain here, this set here, it's mapped to this curvy surface by our parametrization. Okay, essentially what you get here, loosely speaking, very loosely speaking, are curvy parallelograms. Okay? You can think of these little, I guess, these partition sets as little curvy parallelograms. Okay? And, well, if you want to approximate the area of a curvy parallelogram, why not just use a regular parallelogram? Okay? For that, what we do is we have 2 tangent vectors pointing along, say, these 2 lines. Then you've got 2 vectors that span parallelogram. How do you get the area for a parallelogram? Well, you take the cross product and the absolute value. So that's where we're headed. That's where we're headed, okay? One last example. Consider the graph. A natural parametrization, as we talked about before, is the following. What are the tangent vectors? Now, these tangent vectors are going to be very important when you're calculating the surface area of a graph, okay? Okay, so we differentiate in a component-wise fashion. Again, here we're going with respect to x, and then with respect to y. So we're going to get 0, 1, and then, oops, and then f sub y. Where this, by subscripts, of course, I mean the partial derivatives. Okay, so once you have the tangent vectors, if you want to, you can produce a normal vector. All right. If you did do that, you'll get something a little like this. Okay, if you expand that, I'm not going to expand it now, you get something like this. Okay, and that's what we call an upward pointing normal. Okay, the upward pointing because it's got a positive k element or component. Okay, so that's a little bit about parameterized surfaces. Get to know them. Get comfortable with them. Okay, because next week when we start surface integrals, I'm going to assume that you're fairly comfortable with these. Okay, so have a great weekend. I'll see you next week.